Good evening, Laman. Let's start the class for today's session. Right. Today we are going to discuss about the redox reactions. Right. Our discussion today is about redox reactions. So this is going to be the fourth type of reaction we are going to discuss. Right. We had discussed about the acid-base reactions, precipitation reactions, as well as the decomposition reactions. This is the fourth kind, redox reactions. Right. So before we discuss about the redox reactions, let's discuss about the oxidation states, which will be the foundation of redox reactions. All the redox reactions are balanced with the use of oxidation state. So let's discuss about the concept of oxidation state. Right, that is the first discussion to start our discussion about the redox reaction. Right. Okay. Oxidation states. Let's discuss about that thing. Oxidation state. Right. Okay. Oxidation states. What this means? Basically, the oxidation state, we'll write like this, right? The oxidation state. Oxidation state of an atom is actually the number of electrons gained, the number of electrons gained completely or partially number of electrons gained completely or partially. So that is those are the negative oxidation states. Or loses completely or partially. Right, those are the positive oxidation states. By an atom in a considering chemical species. Right? Actually, this is the definition of the oxidation state. So oxidation state of an atom is the number of electrons gained completely or partially, or loses completely or partially by an atom in a considering chemical species. Right? This is the definition. Let's discuss actually what this means. It's like this, Laman. Let's consider the chemical species NH3. Let's consider NH3 and try to come up with the oxidation state of nitrogen there and the hydrogen as well. So if you are to think of NH3, this is the molecule. So here the electrons are not appearing at the center. No? The electrons of the NH bond is not appearing at the center, right? So as the nitrogen is more attractive than the hydrogen, those two electrons are appearing at the nitrogen side, nitrogen's corner. So that nitrogen corner, you are with two electrons like this. So with these two electrons also at the nitrogen side. So this is how the NH3 appears now, because of the difference of nitrogen and hydrogen. Both are electrons at the nitrogen side, right? So when considering this, so you can say this electron, which should be belongs to hydrogen, the second electron which should be belongs to hydrogen, now partially given off by the hydrogen and partially gained by the nitrogen. this electron actually belongs to hydrogen is now partially gained by the nitrogen and partially given off by the hydrogen. So number of electrons gained by nitrogen completely or partially is 1, 2, 3. So electrons gained, no, so that negative oxygen states. So with nitrogen, right, we can say the oxygen state of nitrogen here could be written as -3. By -3, 3 electrons are gained. 3 electrons are gained completely or partially when forming the NH3 by the nitrogen, right? So the idea is gained, right? 3 electrons completely or partially. So nitrogen oxygen state is -3. What about these hydrogens? What about these hydrogens? Let's consider the oxygen state of this hydrogen, right? Oxygen state of that hydrogen. So actually, this electron is actually partially removed or partially, right, lost by the hydrogen, right? This electron is partially used, right, by the hydrogen. So the number of electrons removed or loses by the hydrogen is 1, right? So 1, as the electron is given off by the hydrogen, it is positive, right? Loses completely or partially. If you are losing electron, then those are positive oxygen states. So this is a positive sign, comes as you have given off or loses the electron, right? Loses or given off. How many electrons? 1 electron, completely or partially. So this is the definition of the oxygen state, right? Number of electrons gained or loses completely or partially can be represented as the oxygen state. If you are gaining electrons, those are negative oxygen states. If you are losing electrons, those are positive oxygen states. Normally the oxygen states are written inside brackets. Right? Okay. Right. Let's come up with another example. Let's discuss about the H3O plus. H3O plus. Another example. Right. Discuss about H3O plus, that molecule. Right. H3O plus molecule is like this. Right. You have positive charge as well on top of the oxygen. It's H3O plus, right? I'll write it like this. H3O plus, right? Okay. So how the electrons are appearing in the H3O plus? You clearly see, right? The 2 electrons are on the oxygen side. 2 electrons are on the oxygen side. Actually, the hydrogen's this electron is partially given to the oxygen. Hydrogen's this red colored electron is partially given to the oxygen, right? Let's try to come up with the oxygen state of oxygen here. Oxygen state of oxygen in the H2O plus. So number of electrons gained or removed partially or completely. See, you can see 1, 2, 3. 3 electrons are gained partially and here the plus charge appearing on oxygen, that means it has removed one electron completely. Plus charge on oxygen means it has removed one electron completely. You see, 1, 2, 3, 4, 5, only 5 electrons are appearing with oxygen. That means it has removed one electron completely now. So this oxygen has removed one electron completely and gained 3 electrons, right? Gained 3 electrons, right? Gained 3 electrons partially. Anyway, as a net amount, 3 electrons are gained, 1 electron is removed, so that the net, as a net amount, right, one can say, right, 3 electrons partially gained by oxygen, 1 electron completely removed by oxygen. So one can say the net amount is 2 electrons gained, 2 electrons gained completely or partially. Contribution of complete gaining or partial gaining, both are same, right? Complete or partially, both coming up with the same contribution when considering the oxygen state, right? Okay, so one can write the oxygen state of oxygen as 2 electrons gained. So 2 electrons gained, so that minus, so it is minus 2. Oxygen state of oxygen is minus 2. 2 electrons gained means minus 2 electrons, so that 2, right? What about these hydrogens? When it comes to this hydrogen, you can clearly see this electron is released partially, right? So 1 electron is released. Release means positive, completely or partially, right? So that is why the plus 1 released, given off, 1 electron completely or partially, right? That is what it means. The oxygen state of H3O plus, right? The idea is clear now. The idea is clear, right? Okay. Let's discuss a easy method. Let's discuss a bit more easy method to come up with the oxygen state quickly, right? This is the definition. The things are clear, right? Let's discuss some easy method to come up with this idea, right? Okay, to calculate the oxygen state, let's discuss some easy method by just looking at the Lewis structure, right? Okay, that is the second definition, right? The second definition, right? Let's discuss about the second definition. We have two definitions, Lama, for the oxygen states. Right? The second definition. Second definition. Right? That is said like this. The oxygen state of an atom is, right? The oxygen state of an atom is the charge of the atom, the charge of the atom if all the bonds are considered to be ionic right of the considering chemical species. Right? Oxidation state of an atom is the charge of the atom. The charge of the atom if all the bonds are considered to be ionic, right, of the considering chemical species. Let's discuss what this means. Right? I'll come up with some examples. NH3. This is about the NH3 stuff. Right? This is the NH3. I'm coming up with the same two examples with this method as well, with this definition as well. NH3. Right? If this bond is ionic, if the NH bond is ionic, the electrons are going towards the more electronegative atom. Electrons are going towards the more electronegative atom. So that the hydrogen will lose its electron while nitrogen will get that electron. As the two electrons are going towards the electronegative atom, hydrogen will lose its electron and hydrogen will give off that electron to the nitrogen. So that hydrogen will come up with a positive charge, right? And the nitrogen will come up with a negative charge. See how it appears, right? It's like this now. So if this bond is become ionic, right, that bond becomes ionic, one can write like this now. That bond becomes ionic, right? Both the electrons are going towards nitrogen like this, right? The hydrogen is like this, no? So you had the two electrons like this with that bond, right? You had two electrons like this. One belongs to hydrogen, one belongs to nitrogen. If that is ionic, both are going towards nitrogen, right? So hydrogen will lose its electron. So hydrogen carries a positive charge. Nitrogen will gain that electron. Nitrogen carries a negative charge. With this one, the same stuff. Nitrogen carries a negative charge while hydrogen carries a positive charge. For this bond, stays the same. So what will be the charge on nitrogen? It is -3. Hydrogen, it is +1. So the oxidation state of nitrogen is -3. Hydrogen is +1. Right? You can write like that. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons means -3. That is the idea. You can simply represent this diagram, right? Like this. You can simply represent this diagram like this, giving a positive charge to the electropositive atom of the bond and giving negative charge to the relatively electronegative atom of the bond. For this bond as well, this is minus, this is positive. Give a negative charge to the electronegative atom of the bond, relatively electronegative atom of the bond, give a positive charge to the relatively electropositive atom of the bond, right? That is what happens if that bond is going to be an ionic, right? Okay, so the charge on nitrogen now is -3. Charge on nitrogen is -3. So the oxidation state of nitrogen can be considered as -3. The charge on hydrogen is just +1. So oxidation state of hydrogen here is +1. So that is the charge of the considering atom if all the bonds are considered to be ionic. If all the bonds are considered to be ionic. So you can get rid of these bonds. Right? So NH3 carrying some +1 oxidation state with hydrogens and -3 oxidation states with nitrogens. Right? Okay, that was the idea. Right. Okay, let's discuss another example. So this definition is easy to handle, right? So Just consider this H3O plus. So atom is like this. So the molecule is like this. Let's do the working. If this bond is ionic, hydrogen carries a positive charge, oxygen carries a negative charge. Deuterated atom carries a negative charge, while electropositive atom carries the positive charge. If this bond is ionic, oxygen comes up with the negative charge, hydrogen comes with the positive charge. If this bond is ionic, right, oxygen comes up with the negative charge, hydrogen will come up with the positive charge. So the charge on this oxygen atom, if all the bonds are considered to be ionic, is -1, -2, -3, and this +1. The oxygen state of oxygen is 1, 2, 3, -3, +1, +1 and -3, that is -2, -3, +1. Summation is -2. What about this hydrogen? It is +1 charge on that constituent atom if all the bonds are considered to be ionic. Right? All the hydrogens will carry +1 charges if all the bonds are considered to be ionic, so that the oxygen state of hydrogens are +1. The oxygen will carry a -2 charge if all the bonds are considered to be ionic, so oxygen state of oxygen is going to be -2. So normally we represent the oxygen state inside brackets right now. Okay, let's come up with another example. Right, let's do the next one. Right, third example. H3PO4. You have that molecule, right? So this is how that appears. H3PO4, right? Let's copy the oxygen states of these atoms, right? If the two bonds here are ionic, the electrons are going towards the more negative atom. So for this bond, oxygen comes with a minus charge, phosphorus comes with a positive charge. For the second bond, oxygen gets a minus, phosphorus gets a positive. For this bond, phosphorus gets a positive, oxygen gets a minus. For this bond, phosphorus positive, oxygen minus. Because of the integrated difference, more integrated atom gets a minus charge, while the less integrated atom gets a positive charge. For this bond, phosphorus gets a positive, oxygen gets a minus. Right? So if you are to think of the oxygen state of this oxygen in the H3PO4, the charge on the atom, if all the bonds are considered to be ionic, is -2, -1, -2. Right? So it is -2 here. For this phosphorus, the charge of the phosphorus, if all the bonds are considered to be ionic, it is 1, 2, 3, 4, 5, +5. When writing the oxygen state, always the sign should be indicated, right? Sign should be indicated. The sign carries some meaning, right? Last time we had discussed about that thing. Plus means you had given off. You had given off completely or partially the number of electrons you had given off is indicated by the plus sign. Number of electrons you had gained completely or partially, that is indicated by the minus sign, right? So what about this oxygen? This oxygen, you have to consider all the bonds considered to be ionic, right? So this bond is also ionic. If that is also ionic, oxygen get a minus charge, hydrogen get a positive charge. So we can discuss about the charge of this guy as well. Charge of this oxygen is also -2. So oxygen state of that oxygen also -2. For this thing, it is going to be +1. right? No? So that is how we are supposed to derive the oxygen states by considering the Lewis structure. If the Lewis structure is given, you can come up with the oxygen states by doing this kind of working, right? With all the covalent bonds, you have to mark the plus and negatives, right? Considering the difference there. The more negative atom out of the two atoms of the covalent bond gets the negative charge, while the more positive atom out of the two atoms of the covalent bond gets a positive charge, if that bond is becoming an ionic bond, so that you can calculate the charges around the atom ultimately, right, to come up with the oxygen state of that atom, right? That is the idea, right? Clear, no? So you can do this working, right, for this review for as well. Right. Okay. So we have some questions at the page number 18, right? Appearing at the question number 18. Let's do those things as well, right? To get some clear idea here, right? We can use this technique, Lama. This method is easy to handle, right? When the structure is given, this technique is easy to handle, right? Let's come up with this technique to calculate the oxygen state of those given atoms, right? Right. Now let's discuss the answers for this question, right? Let's try to come up with the answers for this question, right? We have to do some working here. Let's do those and come up with the answers, right? Okay. So the first one is about the H2SO4. Right? Let's do the working, right? So when it comes to these two bonds of the SO, sulfur oxygen, the oxygens will carry minus charges, sulfur will carry the positive charges, right? As the oxygen is more negative than the sulfur, right? Let's mark the charges of all the bonds first, right? Then we can come up with the oxygen state ultimately. So for this sulfur oxygen bond, sulfur comes up with a positive charge, while oxygen comes up with a negative charge. For this bond, oxygen gets a minus, hydrogen gets the positive because of its difference, right? Oxygen is more negative than the hydrogen. For this sulfur oxygen bond, sulfur gets a positive, oxygen gets a negative, as oxygen is more negative than the sulfur. For this bond, oxygen gets a negative, hydrogen gets a positive, right? Let's come up with these bonds as well. For this oxygen sulfur double bond, sulfur gets a positive charge. For the first bond, oxygen gets a negative charge. For the second bond as well, sulfur gets a positive charge, while oxygen gets a negative charge. So I had marked charges for all the bonds here. Let's summarize. So get the summation of the charges to come up with the oxygen states, right? So for the sulfur, the summation of charges is going to be 1, 2, 3, 4, 5, 6, plus 6. For sulfur's oxygen state is going to be plus 6. Right? What about the oxygen in this case? In these oxygens, all the oxygens are coming up with minus 2s, no? Around oxygen, they are with minus 2 charges. So oxygen states of all the oxygens here are minus 2 values. Right now? What about the hydrogens? The hydrogen, the oxygen state of hydrogen here, all the hydrogens are actually plus 1. Right now? That is about the H2SO4. Let's discuss about the NH4 plus. See, first mark the charges for all the covalent bonds as this NH bond. As this NH bond is polar, right? The two atoms are with some electron difference, right? The more electron atom get a negative charge, but and the lesser electron atom gets a positive charge for this bond, right? For this bond, nitrogen gets a negative charge and hydrogen gets a positive charge, as nitrogen is more electron than the hydrogen. For this bond as well, the same. For this bond as well, the same. The summation of charges around nitrogen is now minus 1, minus 2, minus 3, minus 4 and plus 1. Minus 4 and plus 1, that is minus 3. So oxygen state of nitrogen is minus 3 here. For these hydrogens, the oxygen state is equal to +1. So normally we write the oxygen states within brackets, right? Okay, no? Right. Let's come up with this one, HNO3. For this bond, as oxygen is more heavier than the hydrogen, oxygen comes with a negative charge, hydrogen is the positive terminal. So with this one, oxygen is on negative terminal and the nitrogen is the positive terminal. With these, oxygen comes with the positive charge and nitrogen comes with the positive charge and oxygen comes with the negative charge, as oxygens are more heavier than the nitrogens in your NO bonds, right? For this bond as well, nitrogen with a positive and oxygen with a negative. So if you are to add the charges around the oxygens and nitrogens, right? Oxygens, you see, come up with -2 charges. -2 here. Around this oxygen also -2. Around this oxygen also -2, -1, -2. All the oxygens are with -2 oxygen states. When it comes to nitrogen, so you have +1, +2, +3, +4, and this charge is also available, so +5, right? 4 charges, +4 charges due to the bonds, and originally it was there was a +1 charge as well, so that altogether +5 for the nitrogen. Right? What about the hydrogen? Hydrogen carrying +1 oxygen state here. Right now, those are the oxygen states with the HNO3. And this one, just mark the charges of these bonds. Oxygen is more heavier than the carbon, so for the first bond, oxygen minus carbon positive. For the second bond, oxygen minus carbon positive. For the third bond, oxygen minus carbon positive. So the summation of charges around carbon is +1, +2, +3, and -1. That means +2. So the oxygen state of carbon here is +2. What about this? Around oxygen you have -1, -2, -3, and a +1. -3 and +1 is +2. -3 and +1 is -2. Oxygen state of oxygen here is -2. Right now? Okay, next one. Let's come to here. Right, for this one, so the charges around Fe is +2, right? That is simple. Clearly you can see the oxygen state of Fe is then going to be +2. Right, I'll write it here. +2. And with these bonds, let's mark the charges. As the oxygen is more heavier than the carbon, oxygen get a minus, carbon get a positive for both the bonds. For all of these bonds as well, oxygen get a minus, carbon is a positive for the second bond as well. For this single sigma bond as well, carbon is a positive, oxygen get a minus, right? For this carbon oxygen bond as well, carbon get a positive, oxygen get a minus, right? But when considering this CC bond, both the atoms are with same mutuality, the 2.5, 2.5, so no polarity there. So you are not supposed to mark any positive negative signs with this bond, right? No need of marking any signs with this bond because both the atoms coming up with the same mutuality, right? No positive atom or no negative atom if this bond is going to be ionic, right? So actually it's not going to be ionic, no ionic character there, total covalent character here, so no marking of positive negative charges with this bond, right? Okay, so that is all. So we can copy the charges around the atoms now as oxygen states. So with each and every oxygen you will see -2 charges appearing, -2 here as well, -2 here as in -2, right? With all the oxygens they are appearing with -2 charges around them. With the carbons you can clearly see +1, +2, +3. plus 3 is the total charges around carbons, right? So oxygen state of 2 carbons are going to be plus 3s, right? Okay, those are the oxygen states of all the atoms in FeC2O4 ferrous oxalate, right? Let's copy this one. So you clearly see that around the sodium you have a plus 1 charge, so that is the oxygen state of sodium, right? Let's copy the oxygen states of other elements. First mark the charges with this bond. Oxygen gets a minus, carbon gets a positive, as the oxygen is more iterated than the carbon. For this bond as well, carbon positive, oxygen negative. We have 2 bonds here, so 2 positive charges for carbons and 2 negative charges for oxygen because of 2 bonds, right? So altogether all the oxygens are carrying minus 2 charges, right? Minus 2 charges around them. So oxygen state in all these atoms are minus 2 values, and for the carbon you will see 1 plus 1 plus 2 plus 3 plus 4 plus 4. This is a charge appearing around the carbon, so that is oxygen state of carbon, right? Now, so that is, those are the oxygen states of all the atoms of the sodium carbonate, right? The idea is clear, right? No, okay, right? So you can complete the note. Do the working, right? So what we have done here is referred to as, right, the coming up with the oxygen state with the use of the Lewis structure. With the help of the Lewis structure, this is how we are supposed to derive the oxygen state of considering atoms, right? So to copy this method, you should definitely know the Lewis structure of the considering chemical species, or first you have to draw the Lewis structure of the considering chemical species to copy the oxygen state with the use of this method, right? And then even without drawing the Lewis structure, we have a method to copy the oxygen state, right, which is known as the algebraic method. Let's go towards that. But there is another method available to easily calculate the oxygen state, get the oxygen state of considering atoms by just merely looking at the chemical formula, not no need of a Lewis structure for that thing, and that is known as the algebraic method. Let's discuss the theory parts behind that algebraic method, right? Let's discuss about the algebraic method, right, to find out the oxygen state, right? To use before using the algebraic method, right, you should know some basics which will be used in the algebraic method, right? First, let's go through those things, and actually that those are summarized with your table appearing in the page number 19 in your note, right? Yeah, let's go through those things first of all quickly, right? So to use the algebraic method, first you should know some specific oxygen states shown by right, for living atoms, right. This is about that thing first, right, then we can discuss the algebraic method of, right, finding out the oxygen state, right. The first thing, atoms in the elemental form. This is about that thing. Atoms in elemental form, right, atoms in elemental form. See, what is the idea there? Lamai, atoms in the elemental form always comes up with zero oxygen state. Zero oxygen state. See, if you think of sodium, atoms in elemental form, right? Sodium, magnesium, O2, oxygen, Cl2. These are atoms in elemental form. The oxygen state of these guys are always zero. So normally we will indicate the oxygen state, right, with the atom like this, 0, 0. Atoms in the elemental form. Elemental form, only one element is appearing with the uncharged species. That is referred to as the atoms in the elemental form. Is it? That is how the sulfur things are appearing. So sulfur carrying oxygen state 0. Right? That is the idea. Right? So it is clear, no? Now if you think of oxygen, the thing is like this, no? So it is clear, no? No charge separation with same kind of atoms. So oxygen state of this thing is 0, this thing is also 0. With the Cl2, you see. So no charge separation, no plus negative signs, no? So oxygen state of both things are 0. So with this one, see, S8 is this kind of structure. Right? It is structure of S8. Still you see, no charge separations with the bonds. Right? Because same kind of atoms are appearing. So all the atoms carry 0 oxygen state. Right? So atoms in elemental form, right, always oxygen state equals 0. Right? That is the first thing you should know. Atoms in elemental form always carry 0 as the oxygen states. Right? No? That is first thing. Right. Next one. The second thing you should know. Right? Second thing. It is about monoatomic ions. Monoatomic ions. Right? This is about the monoatomic ions. See, these are some examples. Sodium plus, magnesium 2 plus, monoatomic ions. Right? O2 minus, F minus. Right? Then N3 minus, monoatomic ions. Right? Ions with only one atom. Ions with only one atom. That means charged species with only one atom. Monoatomic ions. Ions means charged species. Monoatomic means only with one atom. Right? It could be H minus. See? So the charge around the atom is just the charge of the species, no? So the oxygen state here is +1. For the sodium, oxygen state here is, for the magnesium, +2. For the oxygen, it is -2. The charges around the atom is just the charge of that time. minus 3 for this one. For this one it is minus 1. For the monoatomic ions, right, the oxygen state is equal to the charge of the ion, is equal to the charge of the ion. So for the monoatomic ions, right, oxygen state equals to the charge, equals to the charge. Monoatomic, this guy is sodium plus, guys oxygen state is plus 1. For the O2 minus it is minus 2. For the N3 minus it is minus 3. For the monoatomic ions, oxygen state is always equal to the charge of the ion. Charge of the ion. Right now? Okay. Third thing. Right? Now we are referring to S block elements in compounds. S block elements in compounds. S block elements in compounds, right? Okay. So let's consider the group 1s. Group 1 elements in compounds. Right? So some examples are given. Let's consider those things. NaCl, right? K2SO4, rubidium carbonate, right? When considering these S block compounds, when considering compounds with S block metals, basically I am with group 1, right? Here the oxygen state of this thing, the sodium, the group 1 element, is actually plus 1. Always if you are referring to compounds containing S block, guys, right, the oxygen state of group 1 element is always plus 1. No other oxygen states are available with the group 1 elements, right? No need of drawing the structure. If you see some S block element, basically group 1 element appearing in your compound, its oxygen state is always plus 1. That's it, right? If you have S block element in your compound, right, and if it is group 1 element, its oxidation state is always plus 1. Always plus 1. Always oxygen state equals plus 1 for the group 1 elements in compounds, right? That is the idea. What about the group 2, guys? What about the group 2, guys? These are fundamentals, right? You should know these things to use the algebraic method of finding the oxygen states, right? For group 2 elements, right, that number is always the plus 2. Always oxygen state is equal to plus 2 for the group 2 elements. See some example. So you have given these examples. Right, even some more, right? Any other group 2 guy, barium, carbonate even, right? If you are with a group 2 element in your compound, always this guy's oxygen state is equal to +2. That's it. This guy's oxygen state is equal to, no need of any work in Lamai. Just write it as +2. Right? That is the observed stuff. Oxygen state of group 2 element is always +2. Always +2. For this one, the oxygen state is +2. Right? Okay. So that's a fundamental you should know. Always in compounds, if you are appearing with a group 2 element, that guy carry the +2 oxygen state. That guy carries the +2 oxygen state. Keep that in mind. Those are fundamentals you should know, right? Okay. The next one. Next thing. We are going towards the oxygen states of fluorine. Number 4. Right? Fluorine. Right? In compounds. Fluorine. In compounds or ions, anything. Fluorine in compounds or ions always carry -1. Always oxygen state is -1. These numbers you should know, right? So let's consider, if you take this sodium fluoride, right? Magnesium fluoride, calcium fluoride. For any compound carrying fluorine, for OF2, for any compound carrying fluorine, fluorine comes up with oxygen state -1. Always the oxygen state of fluorine is equal to -1. Oxygen state of fluorine is equal to -1. Right here as well. In chemical species, in compounds or ions, if fluorine appears, always it carries -1. Right? In compounds or ions, if fluorine appears, always it carries -1. Right? That is what you should know with the fluorine. Right? Next one. These are things available in your table there, right? At the page number 19. Number 5 is about hydrogens. Right? Hydrogen in compounds or ions. No, hydrogen in compounds or ions. Right? So if hydrogen is connected with non-metals, it will carry +1 oxygen state. If the hydrogen is connected with metals, it will carry the -1 oxygen state. Right? Right? Normally, hydrogen's value is plus 1. Generally, the oxygen state equals plus 1. Right, if you need some examples, see. Right, if you think of H2O, NH3, even something with the hydrogen CH4, with all the guys, the hydrogen's oxygen state is hydrogen, the hydrogen's oxygen state here. So if you think of this guy, right, see some other thing like CH3OH, alcohol, methanol. With all the guys, the oxygen state of hydrogen is plus 1. With here as well, oxygen state of hydrogen is plus 1. For this one as well, oxygen state of hydrogen is plus 1. For this thing as well, the oxygen state of hydrogen is plus 1. Normally hydrogen comes up with the plus 1 oxygen state, but normally the oxygen state of hydrogen is plus 1, right? The general value is plus 1, but some specific value, the minus 1, will appear only with the metal hydrides. Only with metal hydrides will come up with, right, minus 1. Only with metal hydrides. Generally, the oxygen state is plus 1, but only with metal hydrides you will come up with minus 1 as oxygen state for hydrogen. Right? If you need some examples, see this. When the hydrogen is connected with a metal, sodium hydride, right? So lithium aluminium hydride. Hydrogen is with metals. When hydrogen is available with metals, appearing with metals, they are the oxygen state of hydrogen is referred to as minus 1. Referred to as minus 1 for the oxygen state of hydrogen with metals, right? Metal hydrides. So with some other thing as well, any metal hydride, right? With any metal, calcium hydride, with any metal, if the hydrogen is appearing, the oxygen state of hydrogen is referred to as minus 1, right? So what you should know is hydrogen normally comes up with plus 1 oxygen state. If the hydrogen is appearing with a metal, right, connected to a metal, there the hydrogen's oxygen state is minus 1, right? If not, hydrogen comes with plus 1 oxygen state in compounds and ions, right? So even in ions, right? So if you can think of this ion, right, AlH4 minus ion, in this ion as well, the hydrogen comes up with minus 1, right? As it is appearing with a metal, connected to a metal, right? So metal hydride, so it's minus 1, right? Now that is about the hydrogen. Finally, let's discuss about the oxygen states of oxygen. This is about the oxygen states of oxygens. Number 6. oxygen. In compounds and ions, right? The oxygen's value. Oxygen's general value is generally the oxygen's oxidation state in compounds and ions is referred to as the -2. We had seen that value appearing most of the times with the oxygens, with the examples we had done. With the examples we had done earlier, we had seen oxygen always coming up with -2, hydrogen normally +1, right? We had seen that those things with the examples, no? We had done at the beginning of the lesson, even in the Lewis structures, right? Lewis structure method. So oxygen normally comes with -2, right? Okay, for normal compounds it's -2, right? For the H2O, any kind of compound, right? So even with ions, SO4 2-, with all this stuff, the oxygen's oxygen state is -2. Normally the oxygen's oxygen state is -2. Oxygen state's general value is, for the oxygen, is -2, right? Okay, but few special locations are there. Oxygen carries some other oxygen states than the -2, right? You should know that those things as well. If not those special locations, oxygen state is considered as -2, right? Okay, what are the special locations? So with the peroxides, right, generally the -2. With peroxides, only with peroxides, right, its oxygen state equals -1, right? And with the superoxides as well, such a number will appear. With superoxides, oxygen state of oxygen is will become -1 and 0 with superoxides. Those are special things, right? And with the compound OF2, oxygen carries the +2. Only with the compound OF2, oxygen carries the +2, right? Only with the OF2, I'll write it here. Compound OF2, oxygen state of oxygen is +2. Those are some special things, right? If not, normally consider the oxygen's oxygen state as -2 in the algebraic method. Normally in the algebraic method, we consider the oxygen's oxygen state as -2. With the peroxides like H2O2, Na2O2, sodium peroxide, hydrogen peroxide, you will come up with -1, right? Only with the OF2 compound, oxygen's oxygen state is +2, right? So with superoxides, -1 or 0 will appear, right? Normally consider the oxygen's oxygen state is -2. That is easy, right? That is what you should know, right? Let's use these things what we have learned, these general things what we have learned, to come up with the oxygen states of a considering atom if the Lewis structure is not given by just merely looking at the chemical formula. Let's try to come up with the oxygen states. This is referred to as the algebraic method. Let's see. Right, when using the algebraic method, right, there is a rule. There's a rule. You have to always follow that rule, right? If you're following that rule, you can use the algebraic method to come up with the oxidation state of a unknown atom, right? So what is the rule? The rule means the only rule to follow is this line. The only rule to follow is this. What is the rule? The rule is the summation of oxidation states. The summation of oxidation states of all the atoms. Summation of oxidation states of all atoms in this chemical species should be equal to the charge indicates at the upper right corner of the chemical formula. This is the only rule you should know, right? To use the algebraic method to come up with the oxidation state of unknown. Let's come up with some examples to use this method. Let's try to come up with the oxidation state of phosphorus with the use of this method. Right? Finding out oxidation state of phosphorus in pH3. Let's use this method. So when it's come to pH3, let's consider the phosphorus oxidation state is X. That is what we need to find. pH3, no? So you have three hydrogens. So I'm getting summation of the oxidation states of the species. You have three hydrogens. So hydrogen carry +1, that into 3 hydrogens are there. The summation should be equal to the charge indicated at the upper right corner of the chemical formula, that is 0. Here the charge is 0. The pH3 won't carry any charge. So X is equal to then what? -3. So that is the oxidation state of phosphorus in pH3. See the example. Let's do another thing. Let's come up with the oxidation state of phosphorus in H3PO4. Your second example appearing in your note. Finding the oxidation state of phosphorus in H3PO4. Let's do that. Right? So you have the H3PO4. Right? So the summation should be equal to 0 here. At the upper right corner, the charge is 0. Summation of oxidation state of all the compounds should be equal to 0 now. So you have 3 hydrogens. Right? Hydrogen we know, with non-metals, hydrogen carry +1. So +1 into 3. 3 of those hydrogens are there. Plus the phosphorus, what we need to find. Let's take it as X plus 4 of oxygens. Oxygen normally carries -2. So -2 into 4. Such 4 oxygens are there. So that summation should be equal to the charge indicated in the upper right corner, that is 0. Right? The value is you have minus 3 here, x, and minus 8 here, no? Is 0. So x is equal to plus 5. So oxidation state of phosphorus is plus 5 in H3PO4. Got the idea? So that is for phosphorus and this is for oxygens, right? Okay, so this is how we are supposed to use the algebraic method. Let's use the same thing for a charged species for an ion, right? Use the same technique, right? Let's copy the third example of sulfur of SO4 2-, no? That is your given stuff in the note, no? Find the oxidation state of sulfur in SO4 2- ion. Let's use an ion here. So SO4 2-. So the rules is the summation of oxidation state of all of these atoms should be equal to the charge indicated in the upper right corner, that is -2. Summation of oxidation state of all of these atoms should be equal to -2, right? That is the rule, right? Let's apply that thing. Take the sulfur value as x. 4 oxygens are appearing. So 1 oxygen carry -2. Oxygen's normal value is -2. That thing into 4 as 4 oxygens are appearing. That summation should be equal to -2. The charge indicated at the upper right corner. So you have x here -8. It is -2. -8 comes to this side as +8. +8 -2 is equal to +6. That is the oxidation state of sulfur. So normally oxidation state is represented inside square bracket, inside brackets, right? Okay. Let's copy with another ion, right? Some other examples, right? Finding out oxidation state of carbon, right, in HCO3-. Right, let's do the stuff, right? Bicarbonate time, HCO3-. So the summation of oxidation states of these atoms should be equal to -1, right? As the charge is there as -1. So hydrogen carries +1, right? And carbon, let's take it as x, right? Then 3 of oxygens are there. So 1 oxygen carry -2, such 3 are there, right? That number, the summation is equal to charge indicated at the upper right corner, that is -1. So you have 1 plus x minus 6 is equal to -1. So here -5. -5 goes to other side as +5. +5 minus 1 is +4. So carbon's oxidation state is +4 with the bicarbonate time, right? No? So that is how you're supposed to come up with the oxidation state, right? Okay, right, that is clear, no? Right. So then I'll tell you some easy method. This is the textbook method to use the algebraic method. This is a textbook method of using the algebraic method, right? So I'll tell you another way, right? So to come up with the number very quickly, right? So it's like this. So first of all, Right, I'll copy it like this. First of all, calculate the add the numbers of all the other atoms, right? Actually, other than the atom required. Just get the summation of oxygen states of all the other atoms than the atom required. First take that thing, right? So see, it is actually, so you have 4 oxygens. That means minus 2 into 4 is minus 8, right? Minus 8. So it is minus 8, no? It is minus 8, no? Right? Let's take this value, right? Then you need to add some value to minus 8 to come up as minus 2. So you need to add some value to minus 8 to come up as minus 2. For that, you need to get rid of 6 units from that. Minus 8, no? We need to get rid of 6 units from that. 6 units. So that this should be plus 6. As these guys carry minus 8 to come up with minus 2, this should be plus 6. Plus 6 minus 8 equals to minus 2. Right? That is the other method. So you can just write sulfur toxicity is plus 6. Use the same technique here as well. So this is the thing what you need to come up with, right? So you have minus 6 appearing here. Minus 2 in 3 is minus 6. So you have plus 1 here. Minus 6 plus 1 is minus 5. Minus 5. To come up with minus 1, we need to get rid of 4 units. We need to get rid of 4 units. So plus 4. Plus 4. Always number of units here to achieve this number, and always the sign comes as the opposite sign. Sign comes as the opposite side. It is plus 5, no? Sorry, it is minus 5, no? Minus 6 plus 1 is minus 5, no? Minus 5. So carbon's oxygen state is always a positive value then. Positive. Plus some value. Plus. You need 4 units to come up with minus 1. Plus 4. Right? That is a simple method. Right? I'll copy some other guys as well, with the early examples as well. See? You can use that thing as well, right? It's easy to copy the oxygen state, right? With that method, right? Just do, right, with your mind, right? So see, let's copy the H3PO4, the phosphorus oxygen state. So oxygen state of phosphorus is equal to, so you have minus 4 in minus 2 into 4 is minus 8. Minus 8 here, plus 3 here. Minus 8 plus 3, that is minus 5. So as this is 0, it is plus 5. If you add some plus 5 to minus 5, you become 0. Get the 0 here. Right? So if you need to copy the other examples, see what were the other examples you have done. So SO42 minus, we had done see pH3. So let's copy the pH3 as well. So what you need is this thing. Just calculate the values other than that. Right? Get the summation of the values other than the needed atom. So plus 1 in 3 plus 3. So to copy as 0, phosphorus should carry minus 3. Should carry the minus 3. Normally, the sign will be the opposite. From these, it is plus 3. No? So the phosphorus value should be a minus value. From these, that was about -5, no? -8 plus 3 is -5, no? So phosphorus sign should be plus. Sign is normally going to be the opposite, right? That can be used. So normally we are expecting you to quickly come up with this these values like this, right? Okay, let's do some more examples, right? Which are appearing on page number 20, right? Just do the examples appearing on the page number 20 now. Right, let's do the questions appearing in the page number 20, right? Okay, let's do one by one. This is the first one. MnO2. We are supposed to come up with the oxidation state of manganese here. Let's do the algebraic method. So what we need is the manganese. What we need is the manganese. So let's come up with the oxidation state of manganese. 2 of oxygens carry -4. -2 into 2 is -4. This is -2, no? -2 into 2 is -4. So as the net charge is 0, this should carry +4. That should carry +4. I just write the oxidation state right at the bottom of the corresponding element, right? You have -4 here. As the net charge is 0, the -4 should be cancelled off, so you need to have +4 here, right? So we are looking for this one now. So 4 of oxygens carry -8. -2 into 4 is -8. So this one should carry a plus value, right? -8. So how many units needed to come up with -1? So it is +7. If you add +7 to -8, that will be -1. Right? These are the numbers. Oxygen states. Here. So what we are looking at is the chromium. 7 oxygens carry -14. -2 into 7 is -14. -14. So this value should be +14. Sorry, plus value is -14. This will be a plus value. So you need -2 here. So only 12 units should be cancelled off. -14, you need to cancel off 12 units from that to come up with -2. So +12, right? +12, right? No, if you have to add +12 to -14, you get the -2. So as you are with 2 chromiums here, one chromium get +12 divided by 2. 2 chromiums represent +12. So one chromium, for one chromium, it is divided by 2, that is +6. +6. Right now? See, for this thing, we are looking at chlorine. Oxygen carry -2, hydrogen carry +1. So -2 plus 1 is -1. -1. So chlorine should carry a plus value. As it is -1, it should carry a plus value. So the summation is 0. That means it should be +2. Right now? Okay. See this one? We are looking for phosphorus. Right? 5 of oxygens carry -10. -2 into 5 is -10. So this value should be a plus value. To come up with a 0 here, all the 10 should be cancelled off. So +10. But +10 is represented by 2 phosphorus. So 1 phosphorus. For 1 phosphorus, you need to divide the value by 2. So that is going to be +5 per 1 phosphorus. Per phosphorus. Right now? Okay. What about this thing? They are looking for bromine. 4 oxygens. 4 oxygens carry -8. -2 into 4 is -8. And sodium carry +1. -8 plus 1 is -7. -7. -8 plus 1 is -7. So as this value is 0, this should carry +7. as -7, it should be a plus value, and the value here is 0. All the -7, the 7 units should be cancelled off. It's +7. Right, this value. Let's come up with the manganese here. -2 into 4 is -8. -8. So manganese should carry a plus value as its minus value. -8. So it should be a plus. So how many units should be cancelled off from -8 to come up as -2? 6 units. +6 for the manganese. About this. You have -6 here. -2 into is -6 here. So this should be +6 as the net charge is 0 here. +6. But you have 2 chromiums here. So divided by 2 per 1 chromium. It is +3. For 2 chromiums, it's +6. For 1 chromium, it is +3. Let's do the same for this one. So -8 is there. 4 of -2 means -8. Oxygen means -2, no? So -8. So this value should be a plus value. So you have to get rid of 6 units to come up with -2. Come up as -2. So +6. -8 plus 6 will give you the -2. Right, this chlorine. You will come up with -6 here. -6. -6, so this should be a plus value. So you need to add 5 units to -6 to come up with -1. -6 plus 5 is that -1. This one. 2 fluorines, that means -2. 1 fluorine carries -1. Such 2 are there, -2. So this value should be plus. Right? -2, this way should be plus. So you have -2 here. The net charge should be +1. So it should be +3. If you add +3 to -2, then only you get the +1. Right? This thing. You have -6 here, -6 here. 3 of -2 means -6 here. And +2 here. +1 into 2 is +2. Group 1s carry +1. +1 into 2 is +2. +2 minus 6 means -4. The summation of sodiums and oxygens are -4. So 2 of sulfurs should carry +4 as net charge is 0. But you have 2 sulfurs, so divided by 2 will give you +2 per 1 sulfur. Right, no? So that is how you're supposed to come up with the oxygen states of those atoms. Right? The thing is clear, no? Right. Just complete the stuff. Okay, now let's start the discussion on redox reactions. Right, we had just completed the discussion on oxygen states. Now let's discuss about the redox reactions. Right, I'll take this example to introduce you a redox reaction. Right, so reaction of sodium with Cl2 to produce the NaCl. Let's take this reaction. Right, if you think of this reaction, so sodium and the chlorine are elemental forms, and sodium chloride is kind of an ionic compound. See, it will appear as Na plus signs and Cl minus signs. You know that, right? So if you were to examine this compound, this reaction, right, more closely, you will see something like this. So you are with 2 sodium atoms here, 2 of sodiums, no? And then you are with Cl2. You are with Cl2, no? This is your chlorine, right? So ultimately you are forming 2 of NaCl molecules, Na plus and Cl minus, no? This is the picture, no, of this reaction. This is what happens, no? Right? 2 of sodium atoms reacting with the Cl2 molecule, right, to produce 2 of NaCl compounds, right? So NaCls, no? So with the ionic interactions, they are connected, right? So if you have to see this thing, at the start, you see the sodium atoms are appearing, but at the end, you see the Na plus ions are appearing. When it comes to chlorines, at the start, the atomic form is there, elemental form is there, but at the end, the Cl minus is there. So to happen this, actually what should happen? To convert a sodium to sodium plus, surely an electron should be released from sodium. Electrons should be released from sodium, and to convert the Cl to Cl minus, an electron should be absorbed by chlorine, right? If this kind of electron exchange is to happen, this sodium will convert to Na plus and this chlorine will convert to Cl minus. Such kind of a thing should happen with these 2 atoms as well. This should release some electrons to become Na plus, and that electron should be absorbed by one of the chlorines to become Cl minus, right? So this kind of electron exchange should occur to come up with the products by this reaction, right? So when this kind of electron exchange occurs, right, electron releasements or the electron releasing species are actually undergoing oxidations. Oxidation means what? Oxidation means electron releasement from atoms are considered as oxidation. So oxidation occurs with sodium atoms, and the reduction, electron acceptance, is happening with the chlorine atoms. Reduction. So when this kind of electron transfer occurs, one species, one element or one chemical, one atom will get oxidized, and while the other atom will get reduced. So this kind of a electron exchange where oxidation and a reduction occurs is referred to as a redox reaction. So that is the definition of a redox reaction. If a reaction is to occur by exchange of electrons from one species to other species, that means where oxidation and reduction occurs, is referred to as a redox reaction, right? So in this redox reaction, sodium has oxidized, released electrons, and chlorine has had reduced, right, accepted electrons. Electron acceptance is considered termed as reduction. Electron releasement is termed as oxidation. Oxidation means electron releasement from a species is referred to as the oxidation. Reduction means electron acceptance by a species is referred to as the reduction. So if a oxidation and reduction occurs in a chemical process, it is referred to as a redox reaction, right? That is the simple idea, right? Okay, got the idea? So let's discuss about this oxidation and reduction. more, right? Let's discuss a bit more about the oxidation. Oxidation. So actually we can say electron releasement from an atom is considered as the oxidation, or loss of an electron, loss of electrons is considered as an oxidation, right? Loss of electrons, loss of electron or electrons from a species, atom or ion, is considered as oxidation. That's oxidation, right now. So if you see this example, you see the sodium has released an electron to come up as Na plus. The sodium released an electron to come up as Na plus ultimately. Sodium has released electrons, right? Releasing electrons. This is referred to as the oxidation, right? When an oxidation occurs, let's see what happens to the oxygen state. What happens to the oxygen state of the species? When this kind of electron releasement occurs, oxidation occurs, what happens to the oxygen states? So the sodium's oxygen state here is 0. Here it is +1. Oxygen state of a monoatomic ion is the charge of that thing, +1. Here it is 0. Elemental form carries 0. So when an oxidation occurs, you clearly see the oxygen state of the species increase. Oxygen state of the species increase, right? So you can see that, right? Okay. In oxidation, oxygen state of atom or ion increases, right? Oxygen state increases, right? Okay. And then we are going to give some special name for the species which get oxidized. Here the sodium, right? So normally the species, this could be atom or ion, which get oxidized is referred to as reducing agent. That's the reducing agent. Right? So species which get oxidized is referred to as the reducing agent. So in this case, sodium is your reducing agent. In this case, sodium is your reducing agent. Why we say so? Why we say so, like for the species which get oxidized as the reducing agent? Why we refer like that? The thing is this. Actually, sodium is the one which will get oxidized now. So actually sodium is the one which is actually giving the electrons to the chlorine to get reduced. Sodium is the one which gives the electrons to chlorine to get reduced. So sodium is the agent which reduces the chlorine. Sodium is the agent which reduces the chlorine. So species which get oxidized is the agent which reduces the other species, So we can say the species which get oxidized is the reducing agent. Species which get oxidized is the agent to reduce the other species. So species which get oxidized can be referred to as the reducing agent, which reduces the other species. So sodium is your reducing agent in this reaction, right? This is what you should know about the oxidation, right? Let's discuss the things about the reduction as well. Right. Let's discuss a bit more things about reduction as well, like this. Reduction. Right? Gaining electrons, right? Or gain of an electron is referred to as the reduction. So the chlorine guys, do the reduction means gaining electrons, right? Gain of an electron or electrons by atoms. Or ion is considered as reduction. Is considered as reduction. Gain of an electron, right? So if you have to think of this thing, you clearly see here the Cl2 gained 2 electrons as a chemical species. This is as a chemical species, Cl2 gained 2 electrons to come up as 2 of Cl minus ions. 2 of Cl minus ions. Cl2 is the one. So as a particle, it is Cl2, right? As a particle, it is Cl2. So you have Na plus sodium, guys, individual sodium atoms. But here it is the particle is Cl2. So that guy gains 2 electrons to convert to 2 of Cl minuses, right? So you see, gaining of an electron is referred to as a reduction, right? When reduction occurs, what happens to oxygen states? So this is the elemental form of an atom. Elemental form, that means oxygen state is 0. This is the minus, right? That means the monoatomic ions. So those carries the oxygen state, which is equal to the charge of the species, monoatomic ions. So charge of the species will represent the oxygen state, so -1. So you clearly see the oxygen state has reduced. Oxygen state has reduced. That is what we say reduction. When the oxygen state increases, oxidation. Oxygen state increased, oxidation. Oxygen state increased, oxidation. Oxygen state reduced, reduction. Reduction of oxygen state is referred to as the reduction, right? Okay, right, we can write like that thing as well. So in reduction, oxygen state of atom or ion or species decrease. Oxygen state decrease. And the next thing we can say is actually the species which get produced, the species which get reduced is referred to as the oxidizing agent. Referred to as the oxidizing agent. So one can say the species which get reduced, this thing is the one which attract the electrons from the species which get oxidized. So the species which get reduced is acting as the agent to oxidize the other species. To oxidize the sodium, chlorine is the one who attract the electrons. to oxidize the oxygens, to oxidize the sodiums, fluorine is the one, Cl2 is the one which attract the electrons. So Cl2 here acting as the oxidizing agent is the agent who attract the electrons from the species which get oxidized. So the species which get reduced is referred to as the oxidizing agent, which attract the electrons from the other species to get oxidized. So species which get reduced is referred to as the oxidizing agent, right? Okay, in this case fluorine is your oxidizing agent. Clear, no? Right? These are the things you should know about the redox reactions. Let's discuss about how to balance these redox reactions. That is our main concern, Lama. Right? Balancing chemical reactions. So under that we are coming up with the fourth type here, no? Redox reactions. Let's discuss how to balance redox reactions. Okay, Lama. Let's discuss about redox reaction balancing. Right? Actually, there are two methods available to balance the redox reactions. You clearly see half reaction method, that is the first method, and the second one is oxidation number change method, right? These are the two methods available to balance the redox reactions. Today we are going to discuss about the half reaction method, right? I will discuss this thing with the next session, but today what we are concerning about is the half reaction method of balancing redox reactions. Let's go to that, right? Okay, half reaction method, right? So redox reaction balancing, half reaction balancing method, right? Okay, let's come with that. Half reaction balancing method, right? Okay, this is the first thing, right? So actually there are four steps. There are four steps available. There are four steps to follow when balancing a chemical reaction, redox reaction through this method. Let's discuss one by one, right? Okay, so the four methods, four steps to follow, right? Okay, there are four steps to follow when balancing using this method, right? Okay, I'll take some example and do the balancing, right? I'll take some example and do the balancing using the four steps, right? Okay, all the four steps are appearing in your tute, right? So you can go through the four steps, right? Okay, not four steps, like three steps, no? Major three steps, yeah, major three steps are there. So I'll go through those three steps, right? And let's see how to do the stuff using that, right? Okay, let's concern this example. Let's take this example, right? As an example, let's balance this reaction. Balancing acidic medium reaction of Cr2O7 dichromates reacting with SO2 to form the Cr3 plus and this SO4 minus, right? Let's try to balance this thing with the use of half reaction balancing technique, right? Okay, I will list it. Three steps are there. Three steps are there, right? The first step, step 1, I'll take it as step A, right? I'll take it as step A, right? Step A. Step A is to split the reaction into two halves, right? So step A is split the reaction into two ionic reactions, two halves, two ionic equations. Right? That is the first thing. Right? Two half ionic equations. Right? Split the reaction into two half ionic equations. Right? Okay. So the two half ionic equations are the oxidation half and the reduction half. The two halves. So those are the two halves. Right? Two ionic equations are the oxidation half and the reduction half. Right? So how to come up with that? So normally it's like this, man. So don't look that much about the oxygens and the hydrogens, right? Concern about the other atoms, right? So you clearly see the chromium containing species are available here and here. That is one half. And sulfur containing species are available here and here. So that is the other half. That is how we are supposed to split the reaction into two halves, right? So the first half is this Cr2O7 2 minus convert into 3 Cr3 plus. So I'll write the two halves like this. Split the reaction into two halves. The first half is Cr2O7 2 minus, giving you Cr3 plus. The second half is SO2, giving you the SO4 2 minus. So first split the reaction into two halves, right? This is the chromium containing half and this is the sulfur containing half, right? That is the first thing. So actually this is the reduction half, this is the oxidation half, right? This is the reduction half, the oxidation half. Where the oxidation number increases here, oxidation number decreases here, right? We can check that when doing the process, right? Okay, step B. I complete step B. Step B. Second step, right? Step B is concerned as balancing both the half ionic equations separately. That is what we are supposed to do at this step B, right? Balancing both half ionic reactions, or balancing both half reactions separately, right? To do so, we are going to use 4 steps. To do so, we are going to use 4 steps. Let's do one by one, right? The first thing, right? Let's try to balance this half. Balancing Cr2O7 2 minus goes to Cr3 plus. Let's balance that half, right? First what you need to do is first balance the redox atom. Balance the redox atom. Balance the redox atom or the redox species, right? Redox atom or the redox species, right? So that means the atom which will change the oxygen state. The atom which will change the oxygen state. That is what is mentioned as a redox atom or the redox species. Redox atom or redox species, right? The atom which change the oxygen states, right? So that is definitely chromium, right? This is definitely chromium. So balance that thing. So you have 2 chromiums at this side, you have 1 chromium here, so you need to copy 2 here. That is how to balance the redox atom. Cr2O7 2 minus, at this side only 1 chromium is available, so to balance this thing you need to copy 2 here, balancing the redox atom. Done. Now the second step. Second step, right? Balancing oxygen state with the use of electrons. With the use of electrons, right? Balance the oxygen state using electrons. So we are done up to here, right? We are done up to here. After the first step, you will come up with something like this now. So balancing the oxygen states. See what we can do. First, write the oxygen states of the two species, right? Basically, with the atom, which is going to change its oxygen state, right? So you have 7 oxygens here. 7 oxygens means minus 14 appear in there. 2 of minus 2 into 7, minus 14 appear in there. So with these two guys, you should come up with plus 12, right? So minus 14 is there. So to come up as minus 2, you should need to cancel off 12 units. So plus 12, right? So taking the summation is enough, Lamai. No need of writing it as plus 6 and plus 6. You have 2 chromiums, right? Both are with plus 6s, right? So that means ultimately you will come up with plus 12, right? Summation. Take the summation, right? Here you are with plus 3. With 1 chromium, you have with plus 3. The ions carry its charge as its oxygen state for the monoatomic ions. So 1 chromium carries plus 3. So you have such 2 chromiums. So plus 3 into 2 is plus 6. Take the summation, net value of chromiums here as well as here. So oxygen state is actually going to be changed from plus 12 to plus 6 as 2 chromiums are appearing. 2 plus 6 chromiums are there. So the summation is plus 12 for the oxygen states for the chromium. So as 2 Cr3 pluses are appearing, the summation is plus 6 for the 2 chromiums, right? So to convert the plus 12 to plus 6, you have 6 units of difference. So to balance these 6 units, we are supposed to use electrons. So to balance these 6 units, you need to use 6 electrons. To balance the 6 units of difference with the oxygen states, you need to use 6 electrons. So basically, electrons should be added to the side with least negative nature. Right? To the side with least negative nature, you need to add the electrons, right? Okay. So 6 electrons are needed to add there. So because electrons carry some negative charges, right? So to the side with least negative nature, you need to add the electrons, right? 6 electrons. So that is the second step of balancing a half ionic reaction. Okay. Let's come up with the third step. Step 3, right? Step 3, right? Number 3 is step 3, right? So that is actually balancing the net charge, balancing net charge of the two sides. For that, we use the medium. Using medium. Here as the medium, right? We had to use the H plus because this is acidic medium reaction. So we use the H plus here, right? Okay, let's do the stuff. So up to here, now we are done, right? Up to here, the things are done. Now it's the time to balance the net charge of the two sides, right? What is the charge here? The net charge here is you have 6 particles of minus 1. Minus 6. You have 1 particle of minus 2. So minus 2, minus 6 and minus 2. The charge here is minus 8. Charge here is minus 8 at the left hand side. What about this side? You have 2 particles of plus 3. 2 particles of plus 3. So that is, the charge is plus 6. 2 particles of plus 3. Right? It's like you have Cr3 plus and another Cr3 plus. 2 particles of plus 3. That means altogether plus 6 will be the charge at that side. Right? Okay. So you need to balance the charge. So you have 14 units of difference. 14 units of difference. Minus 8 and plus 6. See? Minus 8 and plus 6. It's like this, no? So you have the minus 8. You have the plus 6 here. So going to 0, you achieve the stuff. So between these two values, you have 14 units of difference. 6 units appearing here, 8 units appearing here, 14 units of difference. So you need to add 14 H pluses. 14 H pluses to each side. As H pluses are positively charged species, you need to add the H pluses to the side with least positive nature. To the side with least positive nature, you need to add the H pluses, right? So when you are balancing a scale, right, you need to add the stuff to the side which is actually lack of those stuff, no, right? So that is what we are doing. So the 14 H pluses are added to the side with least positive nature, as the H pluses are carrying some positive charges. So the side with least positive nature is this side, right? Least positive nature. So you are supposed to add 14 H pluses to that side, right? 14 H pluses to that side, right? Okay, that is the third step, right? Okay, let's come up with the fourth step now. Step 4 of balancing a half ionic equation. Step 4 is actually balancing the hydrogens or oxygens. Balancing hydrogens or oxygens. For that, we use water molecules. So using water molecules, you can balance the hydrogens or the oxygens, right? So up to here is now done, right? So here the thing is done now. So what we need to do is now to balance the hydrogens or the oxygens. Let's balance the hydrogens. That is enough. Balancing one is enough, right? You have 14 hydrogens at this side. So you have number of hydrogens is 14. At this side, number of hydrogens is 0. So you have 14 units of difference. 14 units of difference between the two sides of hydrogen, right? So you need to add 7 H2O molecules. To provide 14 hydrogens, 7 H2O molecules are needed. So 1 H2O molecule carries 2 hydrogens, no? So 7 H2O molecules can provide 14 hydrogens. So we need to add the H2Os to the side with least hydrogens. So here is the side with least hydrogens. To that side, we need to add the required number of H2Os. So 7 H2Os. Right now. So that is how we are supposed to come up with H2Os, right, to balance the hydrogens. So this is our first half reaction. Actually, it is the reduction half reaction. So we can write it as 1. Reduction half reaction. Right? So we clearly so the oxygen state decreases going from reactant products. So that is a reduction. So this is the balance of the reduction half reaction of the net reaction, right? Okay, right. Just complete this stuff, right? Just write these 4 steps at the space given there. At this step B, at page 22, you have some space. Just complete this 4 steps. Right now, okay, let's balance the second ionic reaction as well. The oxidation half. Let's balance the oxidation half as well. So at this step B, you have to balance both the half ionic reactions, right? So this is balanced now. So this is done. This is done now, right? Now it's the time to balance the SO2 convert into SO4 minus. Let's balance that stuff as well, right? So balancing that term. The second thing. Just do the same things, same 4 steps to conversion of SO2 to SO42 minus. Right? So here I am actually balancing the second half reaction, right? Which is actually SO2 convert into SO42 minus. This balance stuff. So balancing the redox species. So there first we need to think of the redox atom, right? So one sulfur atom, that is balanced. Balancing the redox species or redox atom is balanced, right? That is done. Secondly, balancing the oxidation states. Let's do the step. So SO2 convert into SO42 minus. For that you need to use electrons, right? First write the oxygen states to balance. So you have two oxygens. Right? Earlier this is balanced, right? So you have two oxygens. That means minus 2 into 2 is minus 4. So sulfur should carry plus 4 here as the oxygen state. Here minus 2 into 4 is minus 8 here as oxygens. So sulfur should carry plus 6. So those are two oxygen states. So to balance this thing, we are supposed to use the electrons E minus, right? So E minus should be added to the side with least negative nature. Here you clearly see 2 units of difference. So the side with least negative nature is this side, least negative nature. So to that side, the electrons added, right? As you have it, 2 units of difference, 2 electrons should be added to the side with least negative nature, as electrons are negatively charged, right? Let's copy this one. So balancing the oxygen state is done. So then the reaction appears like this. After the balancing of oxygen states, the reaction would appear like this, right? Let's try to balance the net charge using the medium. This medium is acidic, right? That is what they have mentioned at the beginning of the question, right? So let's balance the net charge. So charge here is 0. Charge at this side is 0 because you have one particle without a charge. The charge is 0 then. So you have one particle with minus 2 charge. So you have two particles with minus 1 charge. Two particles with minus 1 charge means minus 2 from this one and minus 2 from this one. So minus 4 is the net charge at the right hand side. Right hand side minus 4 is the charge. So to balance the charge, right, you are going to use the medium, that is H plus in this case. So 4 units of difference is there. 4 units of difference means you need to add 4 H pluses. So to the side with least positive nature, as ions are positively charged, right? So the side with least positive nature is this side, right? To that side you need to add the difference 4 of H pluses. Right now, that is how we are supposed to balance the charge. Finally, we need to balance the hydrogens and the oxygens in the of two sides, right? So up to now, the thing is done. Just balance the hydrogens and the oxygens. Just balance the hydrogens. Balancing one is enough, right? So number of hydrogens here is 0 at this side. At this side, you have 4 hydrogens. So 4 units of difference with the hydrogens. So you need 2 H2O molecules to provide 4 hydrogens, right? 2 H2O molecules. So you need to add the 2 H2O molecules to the side with least hydrogens. To the side with least hydrogens. So that is this side. So just add 2 H2O molecules there. So that is how we are supposed to balance that second half of the reaction, right? So this is the second half reaction, right? Okay. So we are done with the 2 half reactions now, right? So just complete the stuff. Actually, that is appearing in your note, right? At the page number 23, the balancing steps are written, right? No? Right. So that is all about the step B, balancing both half reactions separately. Okay. So I'll write the results here. I'll write the 2 results of step B. After doing so, right, we'll come up with these things now, right? 14 H pluses and Cr2O7 2 minus penton to give you 2 of Cr3 plus, right? And 7 of H2O, and you had 6 of electrons as well here, no? 14 H pluses as well as 6 of E minuses, no? That was the case, no? Right? Okay. Right. That was the oxidation half, and the reduction half was like, right, 2 of H2O plus SO2 giving you the SO42 minus and 2 electrons plus, right, the 4 of H plus, no? Yes. Those were the 2, right, ionic equations, right? This is one, this was the second, right? No? That was what we had get after the step B, right? Okay. Next one, step C. Combine these two stuff, right? Step C. Step C means actually we are supposed to combine the 2 half reactions to get the simplified balance equation, right? Combine the 2 half ionic reactions right? Combine 2 half ionic reactions, or half ionic reactions to get the balance equation. To get the balanced ionic reaction. To get the balanced ionic reaction, right? See how to do so. So basically, in a reaction, right, you won't come up with electrons as reactants or products. As reactants or products, you won't come up with electrons in a reaction, right? So you won't see the appearance of electrons at the reactant side or the product side in a normal equation. So in redox equations as well, you won't see the appearance of electrons at the reactant side as well as the product side of the reaction, right? So that our main idea here is to get rid of these electrons, right, appearing with the two half reactions. We need to get rid of these electrons appearing with the two half reactions to come up with the balanced ionic reaction, right? So what we can do? So basically, if we are to multiply the second equation, by 3, that will give you a 6 electron value here. If you multiply the second equation by 3, you will get 6 electrons here. Then if you add that into the first equation, what will happen? 6 electrons at the product side will cancel off with the 6 electrons at the reactant side. So that is the algebraic operation I'm supposed to do here to cancel off the electrons, right? So let's do the stuff. For that, normally we use the least common multiple, right? Least common multiple, right? That is the idea. So least common multiple between these two guys are the 6. So to come up with 6, we need to multiply this thing with 3, right? So that we can cancel off if you have to add the two stuff then, right? So it's like this, combining the two half reactions to get the balanced ionic equation. So what you can do is just take the equation 1 and add the second equation multiplied by 3, the first equation, right? With this mathematical operation, you can get rid of electrons. That is what we are supposed to do to come up with the ionic reaction, balanced ionic reaction, right? Let's do the stuff, right? So that will give you what? So just one. First write the things at the left hand side, then we can write the things at the right hand side afterwards, right? First 14 H pluses are appearing here, right? First let's complete the redox species, the chromium guy and the sulfur guy at the left hand side. Ultimately you can balance the H pluses and the H2Os because both those will appear with both the equations. First complete for these guys. So first thing is just use as it is. So chromate Cr2O7 dichromate is written, plus second thing is multiplied by 3, so 3 of SO2 will appear, right? And the first thing is multiplied by 1, just 1, and this will be written as it is, Cr3 plus. Second thing is multiplied by 3, so 3 of SO4 2 minus, right? You are not supposed to write the electrons, but we are doing this operation to get rid of electrons, right? Okay, then write in the H pluses and the H2Os, right? So when you are taking the first equation, you have 14 H pluses at the left hand side. When you are multiplying the second equation by 3, you will get, right, this into 3 is 12 H pluses. This into 3 is multiplying second equation 3, right? This into 3 is 12 H pluses. 12 H pluses appear near the right hand side. 14 H pluses appear near the left hand side. So at the left hand side, it will remain 2 H pluses. 14 here. This becomes 12 as it is multiplied by 3, right? So 2 will remain at this side. Finally, the H2O balancing, right? You are with 7 H2Os at this side. This will be multiplied by 3, second equation. That means 6 H2Os, 6 H2Os at this side, 7 H2Os at this side. So that means 6 will cancel off and 1 H2O will remain at this side, right? So this is the balanced ionic equation. This is the balanced ionic equation, right? Now that is how we are supposed to come up with the balanced ionic equation, right? Now that is step C, right? Done. Okay, right. After this, if they have provided the acid responsible for provide the H plus and the compound which is responsible to provide the dichromate ions, then we can come up with the balanced chemical reaction as well, right? So this is just completion of this question, right? But if they have provided the chemical species which is going to supply H plus, and the chemical species, the compound which supplies this thing, so we can come up with the balanced chemical reaction as well, right? So what we are supposed to do, so let's do that as well, right? අපි එකත් complete කරමුද, right? Okay, let's do the stuff as well. Under the step C, let's try to come up with the balanced chemical reaction as well. Okay, under step C, we can complete the stuff as well. This is the half ionic reaction, right? This is referred to as the, right, balanced ionic reaction. Right, let's try to come up with the balanced chemical reaction as well, right? See whether we can come up with the balanced chemical reaction as well, right? So I write that thing there, right? So yes, so let's come up with the balanced chemical reaction, right? So basically balanced chemical reaction means what we are supposed to do is actually we have to get rid of these ions in your ionic reaction, and we need to come up with some neutral species, some compound synthesis of ions, right? So with the balanced chemical reaction, all the species indicated should come as compounds. No charges should appear with any of the species when it comes to balanced chemical reaction. Let's try to develop that thing, right? So let's assume, so they need to give that, right? Let's assume, right? Just assume H plus is provided by H2SO4 and Cr2O72 minus is provided by potassium dichromate, right? Then let's try to come up with the balanced chemical reaction, right? So your ionic reaction is given like this. I write the reaction first of all. So your ionic reaction is provided like this: 2 of H plus Cr2O72 minus 3 of SO2, this is 2 of Cr3 plus. This was your ionic equation. Let's come up with the chemical reaction. Right? Let's come up with the balanced chemical reaction. See, instead of H plus, you need to write the H2SO4 now. Instead of H plus, you need to write the H2SO4 now. And instead of dichromate, you need to write the potassium dichromate now, right? Let's see. So to provide two of H pluses, you need one H2SO4 molecule. To provide two of H pluses, you need one H2SO4 molecule, right? So that I have added one SO4 minus ion by hand, right? By hand, I have added one SO4 minus ion. I have added one SO4 minus ion by hand, right? So that definitely I need to add that thing to this side as well. I need to add this one SO4 minus which I have added by hand to the other side as well to balance the stuff, right? So now it is not balanced, right? As I have added SO4 minus ion to the left hand side, you need to add that thing to right hand side as well, right? Okay. So dichromates will be provided by K2Cr2O7. So to give you one dichromate ion, you need one of K2Cr2O7. So by hand, I have added two of K plus ions. Two of K plus ions. So that balanced ionic equation, I have added two of K plus ions, right? To come up with the balanced chemical reaction, right? So uncharged species will be written as it is. Uncharged species will be written as it is, right? Okay, right. Now we need to add these guys to the other side as well. These guys to the other side as well, right? So two of Cr plus are there. So Cr plus, this charge should be neutralized. This charge should be neutralized. To neutralize that charge, we have minus ions. In my bag, I have one SO4 minus ion, and in this side, you have three SO4 minus ions. So you have altogether four SO4 minus ions to neutralize these positive charges, right? So the chromate combines with sulfate to give you chromium sulfate, right? CrSO4. Chromiums combined with sulfate to give you the chromium sulfate. So how to write that thing? Chromium's valency will be added, right, written with the sulfate ion. Chromium's valency will be written with the sulfate ion, and sulfate's valency will be written with the chromium ion, right? SO4 minus Cr3 plus, right? With this compound, you are representing the two chromiums. We are happy, right? So with this stuff, right? With this stuff, all the SO4 minus ions are written here, this side, guys, right? So these two are written now. That means with this one. So some water is there, and ultimately, what I have added by hand should be written to the should be given to the other side as well, right? To balance the stuff. So one SO4 minus and two of K pluses are there. So two of K plus and the one SO4 minus. So K plus and SO4 minus combines to form what? SO4 minus, SO4 minus, exchange the valencies K2SO4, K plus. So it is the K2SO4, and that will consume all the K pluses and SO4 minuses I have added to this side, right? So that is the equation. So it is balanced. So this is referred to as the balanced chemical equation, right now. So you can complete this stuff as well. So you have some space at the page number 23. Just complete this stuff. Right now. Okay, let's do one example there. So at the page number 31, at the page number 31, you have provided some 10 questions. Question number 10. If you go to the question number 10, you have some balancing questions, right? Go to those, right? I'll do the first one here to have you some idea, right? And you're supposed to complete up to the 10th question, right? Okay. Okay. Gain an idea. I'll do the first one. First thing to do is step A. Step A is actually coming up with the two halves of this reaction. Two halves of this reaction, right? So you clearly see. So you have manganese containing species here as well as here. This is one half of the reaction, right? You have the carbon containing species here and here. So this is the second half of the reaction. Those are the two halves. of the reaction. So step A is to write those two things. So first half reaction is about MnO4 minus convert into Mn2 plus. Second half is about C2O4 minus convert into CO2. Right? Two halves. Let's complete this off. Right? Step B. Step B is actually balancing these two halves. Right? One after the other. Right? Let's balance. Right? Okay. First balancing the MnO4 minus goes to Mn2 plus. See? Okay, let's follow the 4 steps there. First thing, balancing the redox atom. Manganese is balanced. Balancing the redox atom is done. Second thing, balancing the oxygen state. Balancing the oxygen state. So it is minus 8. So you have minus 1 here. So that should come up with plus 7 here. Plus 7. Here, plus 2. The monoatomic ion, right? So oxygen state difference is 5 units. So you need to add 5 electrons to balance the oxygen states. So 5 electrons should be added to the side with least negative nature. So 5 electrons should be added here. Next step. Next step is to balance the charges, net charge. Balance the net charge. So you have minus 5 and minus 1, minus 6. Altogether minus 6 at the left hand side, minus 6 at the left hand side. Here you have plus 2 at the right hand side. Right? You have minus 5 and minus 1, minus 6 at the left hand side. You have what? Plus 2 at the right hand side. Right? So the difference is 8 units. Minus 2 to, sorry, plus 2 to plus, minus 6 is, difference is 8 units. 8 units of difference between the two sides, the charges, right? So 8 of H pluses needed to be added. Medium is acidic. 8 of H pluses needed to be added to the side with least positive nature. The side is least positive nature is this, right? So H pluses, 8 H pluses should be added there. Then balancing the hydrogens with use of H2O. At the left hand side you have 8 hydrogens, at the right hand side no hydrogens. So 8 units of difference hydrogens, right? So you need to add 4 H2O molecules there. Right now, that is done. That is the balancing of first half ionic equation. Right. The second one is balance the second half ionic equation. Right. First step, balancing the redox species. So you have 2 carbons. So you have only 1 carbon here. So have to put 2 here. Right. Balancing the redox species. Balancing the redox atom is done. Now balancing the oxygen states. So minus 8 is there. 4 of oxygen is minus 8 is there. So to come up with minus 2 should have plus 6 coming with 2 carbons. Summation of 2 carbons, the summation of oxygens of 2 carbons should be plus 6. To come up with minus 2 as this is minus 8. So you have 1 carbon here. So anyway you have 2 oxygens. 2 oxygens means minus 4. 2 oxygens means minus 4. Minus 2 into 2 minus 4. So 1 carbon carries plus 4 as is 0. 1 carbon carries plus 4. Such 2 carbons are there. Such 2 carbons are there. So that is plus 8. Plus 8, right? Plus 8. Minus 4. So that 1 carbon carries plus 4. Such 2 carbons are there. So plus 8. So 2 units of difference. 2 units of difference. So you need to use 2 electrons there. 2 electrons there to balance the oxygen states. So 2 electrons should be added to the side with least negative nature. Side with least negative nature. Least negative nature means, right, greater positive nature. So 2 electrons should be added here. So minus 8 minus 2 means plus 6. That is balanced, right? Oxygen states are balanced. Right. Next step, balancing net charge of 2 sides. Net charge of this thing is minus 2. So you have 1 particle. You have 1 particle with minus 2 charge. So it's like this, no? You have 1 particle with minus 2 charge. So here you have two particles with -1 charge. You have two particles with -1 charge, right? So electrons, right? Here you have one particle with -2 charge. So net charge is -2 here, here as well. So charge is balanced. So no need of using the medium there. Third step done. Fourth step, balancing the hydrogens. So you don't see hydrogens appearing here as well as here. No need of balancing hydrogens there. No need of adding H2O there, right? Okay. So the second half equation, half ion equation is also done, right? So this is the number 1. This is number 2, right? Okay. Now write in the balanced ionic equation. So balanced ionic equation. Let's try this stuff, right? To come up with the balanced ionic equation, you need to get rid of these electrons. 5 electrons are there, here 2 electrons are there, so you need to get rid of these things, right? So first think of the least common multiple, that is 10. So to come up with 10, you need to multiply this thing with 5, right? This thing with 5 and this thing with 2, right? So what you need to do is, to come up with the balanced ionic equation, you need to multiply the first equation from 2 and you have to add multiplying the second equation by 5. This mathematical operation will get rid of electrons from your equation, right? So let's write this stuff. First write the redox species. Let's first balance the redox species. After that you can balance the hydrogens and H2Os, right? First balance the redox species at the left hand side, then the right hand side, right? First the redox species at the left hand side. So first equation is going to be multiplied by 2. So 2 of MnO4 minus, and second thing is multiplied by 5 of C2O42 minus. This will be multiplied by 2 of Mn2 plus. This thing with 5, that means 10 of CO2, right? Okay. Then no need of writing electrons. Then after doing that, we are supposed to balance the hydrogens and water molecules. So first thing multiplied by 2 means 16 H pluses. You don't see H pluses appearing at the second equation, so 16 H pluses can be written here. Second, at this side 8 H2Os will appear, right? That is all about the H pluses and H2Os, right? That is the balanced ionic equation, right? Finally, we are supposed to come up with balanced chemical reaction or equation. Balanced chemical equation or balanced chemical reaction. Let's try to come up with that thing, right? So H pluses are provided by H2SO4. H pluses are provided by H2SO4. So to provide 16 H pluses, you need 8 H2SO4 molecules. To provide 16 H pluses, you need 8 H2SO4 molecules, right? Okay. As we have written 8 H2SO4 molecules, right? So you have added 8 sulfate molecules by hand. You have added 8 sulfate molecules by hand. Just write that thing, because all of those things should be written at the other side as well, right? Okay. Then to provide MnO4 minus ions, you need to come up with KMnO4. So to provide 2 of MnO4 minus ions, 2 of KMnO4 molecules are needed. That means by hand you have added 2 of K pluses, 2 of K pluses, right? So those things should be added to the other side as well. So here you need 5 of oxalate ions. So oxalate ions are provided by K2C2O4, right? So that 5 of K2C2O4 molecules should be added there. So that I have added 10 K plus ions by hand. So 10 K plus ions by hand. 5 of 2 K pluses are there. that into 5, 10k plus ions. So 10 plus 2 is 12k plus ions added. Earlier that was the answer was 2, 12k plus ions added by hand. So we need to apply those things to the other side as well. Right, let's balance the stuff at the left hand side. 2 of Mn 2 pluses. So to balance, so to neutralize the Mn 2 plus, right? So we need to neutralize all the things when coming up with the balanced chemical equation. To neutralize the 2 of Mn 2 pluses, right? So we need to come up with some sulfate ions which are with us in our bag. In our bag we have 8 sulfate ions to use balancing this stuff, right, at the right hand side. So we can provide 2 of SO4 2 minus ions from our bags to come up with 2 of MnSO4, right? Right now, to provide 2 Mn2 plus ions, you need 2 of MnSO4, right? Okay, right. Next one. So 10 of CO2s can be written like this. So before that, Lamai, when you have added some 2 SO4 2 minus ions there, just remove 2 from here. Just remove 2 from here. You have 8. You had 8, no? Now you had only 6. Now you had only 6 because 2 are used to neutralize the Mn2 pluses, right? So only 6 are here, and 12 of K pluses are here, right? Okay. Then 8 of H2Os. Just write the neutralized species as they are, right? Then finally, all the things here should be written at the other side as well. So 6 of SO4 2 minus 1, 12 of K pluses. So that will combine to give you K2SO4, right? Potassium ions and the sulfate ions will combine to give you the K2SO4. Sulfate valency will be written with the potassium. Potassium valency will be written with sulfate, right? K2SO4. So how many of those needed? So we have 6 of sulfates and 12 of K pluses. So that will give you 6 of K2SO4s. 6 of K2SO4s. So that means all of these guys are used at the right hand side as well. So that is your balanced chemical equation. Right? It is the balanced chemical equation right now. Okay, that is how you are supposed to come up with this kind of a problem solving, right? Okay, let's complete the question. Okay, Lamai, let's do the fourth question as well. Question number 4 as well. Let's balance the stuff, right? I thought of balancing that thing as well because it is the basic medium balancing, right? So to get some idea about the basic medium as well, let's balance the fourth thing as well, right? Okay, so here in a basic medium, aluminium reacting with the NO3 minus to give you the aluminate and then the NH3. So to come up with the balanced chemical reaction, they have provided NaOH to provide the OH minus, aluminium, and the NaNO3 to provide the NO3 minus ions, right? Okay, let's try to balance the this equation, right, using the half reaction balancing method. Okay, first thing, to come up with the 2 halves of the reaction, right? So you clearly see this is the aluminium containing species, so AlO2 minus, that is also aluminium containing species. So this is one half and this is the other half which contains the nitrogen, right? So aluminium containing half and the nitrogen containing half, those are the 2 halves, right? So let's write the 2 stuff, right? So the first half is aluminium converting to AlO2 minus. The second half of this reaction is actually NO3 minus converting to NH3. Let's balance the 2 halves now. The step is done, right? Separating the 2 halves. Then balancing the 2 ionic reactions, 2 halves, half ionic reactions, one by one. First balance this one, right? So first thing to do is actually, first we need to balance the redox species. So one aluminium, redox species is balanced. Then balancing the oxygen states. Here the oxygen state is 0, just the elemental form, oxygen state is 0. Here, the oxygen state is what? See, so you have two oxygens. Two oxygens means -4. Two oxygens means -4. So this should have positive number. -4, no? Positive number. What should be the number? It should be +3. So -4 plus 3 will give you the minus. -4 plus 3 will give you the minus, right? Okay. The oxygen state difference is 3 units. So you need to come up with 3 electrons. You need to come up with 3 electrons to balance the oxygen states, right? To each side. 3 electrons to the side with least negative nature. Electrons are negative, no? To the side with least negative nature, right? So 3 electrons should be added to this side, right? +3 and the -3 will give you 0, right? Okay. Next step. Next step is balancing the net charge of the two sides. So at this side it is 0. At this side you have one particle with -1 and you have 3 particles with -1s, right? So altogether net charge is -1, -2, -4, right? -4. Here net charge is 0. So 0, other side -4, right? Okay. So 4 units of difference, 4 units of difference. So you need to come up with 4 of OH minus signs, 4 of OH minus signs, right? As the medium is basic. 4 of OH minus signs to each side. To the side with least negative nature in this side. To the side with least negative nature, because OH minus carrying some negative charge, right? So to the side with least negative nature. So that is this side, right? So you need to add some 4 of OH minuses that side. Right now? -4. Okay. Next stuff. Balancing the hydrogens. So you have 4 hydrogens at this side. You have no hydrogens at this side. So you need to come up with 2 H2 molecules. So 4 hydrogens, 0 hydrogens. That means 4 units of difference with the hydrogens. So 2 H2 molecules are needed to this side. Right now. So the first half ion equation is balanced. Let's come up with the second one. First step is to balance the redox atom. 1 nitrogen, it is balanced. Then balancing the oxygen states. So you have -6 here. -2 into 3 is -6. You have -1 appearing here, so that this should be +5. +5, the oxygen state of nitrogen. Normally the oxygen states are written within brackets, right? Okay, +5. So here you have +3 here. So the nitrogen should carry -3 here. Neutralize the charges, right? Oxygen states, right? So how many units of difference? +5 and -3. So you have the -3, you have the +5. So along with 0, you have 3 units of difference here, you have 5 units of difference here, altogether 8 units of difference. 8 units of difference, right? Okay. So 8 units of difference there. So 8 electrons are needed to the side with least negative nature. To the side with least negative nature. So 8 electrons are needed at this side. Just write the electrons as E minus, then it is very easy to balance the charges there, right? E minus, right? Next step is to balance the charges of two sides. So this side you have 8 particles of -1, here 1 particle of -1, altogether -9 there. -8, -1 is -9. So -1, 9 at this side. Here 1 particle with 0 charge. So charge is 0. So difference is 9 units. So you need 9 OH minus ions, as the medium is OH minus. So charge balancing is done with the medium here. Medium is basic, right? NH medium, basic medium. So 9 units of difference. So 9 OH minuses are needed to side with least negative nature, right? 9 OH minuses are needed here, right? Okay. Finally, the hydrogen balancing. How many hydrogens are needed to each side? So at this side, no, you have 0 hydrogens, right? At this side, you have 9, and here also 3 is there. So 12 hydrogens. So 2 units of difference. So that means 6 H2 molecules are needed. 6 H2 molecules are needed to each side. To the side with least hydrogens. So this is that side, right? So 12 H2 molecules are needed. Right now, 12 H2 molecules are needed there, right? not 12, it's 6, no, it's 6, right? So 12 hydrogens can be divided by 6 water molecules, sorry, 6 water molecules, right? Okay, that is how we are supposed to balance there, right? Okay, the two half ionic reactions are balanced. Two half ionic reactions are balanced, right? Now it's the time to come up with the ionic equation, right? Coming up with the ionic equation. Balanced ionic reaction or equation, both are okay, right? Right. So to come up with the balanced ionic equation or balanced ionic reaction, right? So what we need to do is, actually we need to cancel off the electrons appearing at the both sides, right? So you have 3 electrons here. So you have 8 electrons here. So least common multiple is going to be 24. Least common multiple of 8 and 3 is 24. To come up with 24, you need to multiply the first equation by 8. Multiply the first equation by 8. And you have to add the second equation there. Second equation multiplied by 3. To come up with 24, it should be multiplied by 3. Consider least common multiple and multiply the number of electrons to get the least common multiple, right? Okay, let's do this mathematical operation to these two equations, right? To come up with the balanced ionic reaction. Right, let's do the stuff. First for the Redox species, right? So first thing should be multiplied by 8. So 8 aluminium plus second thing should be multiplied by 3. 3 of NO3 minus, giving you first thing with 8 aluminate ions, second thing with 3 of ammonia, and we no need to consider the electrons because we do this mathematical operation to get rid of electrons, right? So no need of concern in that. Let's concern the OH minus and the H2Os, right? So at the left hand side, as it is multiplying with 8, 32 OH minuses are available, right? As the first equation is multiplied by 8, right? 8 into 4 is 32 OH minuses are available at the left hand side, right? At the right. So as this one is multiplying with 3, right? 27 OH minuses are available. 27 OH minuses are available. As this one is multiplying with 3, right? 27 OH minuses are available. So 32 here, 27 here. So 27 will be cancelled off, right? By having 5 here, right? So 5 of OH minuses at this side, right? No? Okay. Finally, the water molecules. So this thing is multiplied by 8. So 16 H2Os, right? And the second thing is multiplied by 3, right? 3. That means here 18 multiplied by 3 means second thing with 3 at this side 18 H2Os are there. First thing is multiplied by 8 means 8 into is 16, right? So 18 and 16, that means 16 will be cancelled off, right? So remaining number of H2Os will be 2 at this side, right? So 2 of H2O. That is the half ionic reaction. So both the medium and the H2O could be at the same side, right? No worries, right? Both the medium and the H2O could be at the same side. No worries, right? That could happen, right? Okay. That is all about the balanced ionic reaction, right? Let's complete the balanced chemical reaction by using this balance chemical reaction, right? No? Balanced chemical reaction, that's right. So uncharged species could be written like as it is, right? So 2 of H2O, this 2 of H2O, uncharged species, plus 5 of OH minuses. So OH minuses are provided by NaOH. So we need to write it as 5 of NaOH, right? 5 of NaOH, as OH minuses are provided by NaOH as they have given, right? So with this one, I have added 5 Na plus ions by hand. I have added 5 Na plus ions by hand, right? 5 Na plus ions by hand, right? Keep that in mind, right? So 8 aluminiums are there. Just write that thing as it is uncharged species. Write them as it is, right? As they are, right? Okay. So nitrates are provided as sodium nitrates. So we need to come up with 3 nitrates. So 3 of sodium nitrates should be written there. So with this, we have added another 3 Na plus ions by hand, right? So altogether 5, and that 3 gives you 8 Na plus ions, right? Okay. Right. So you can use those stuff to neutralize the species available at the right hand side, right? So 8 H plus Na pluses are there, 8 AlO2 minuses are there. So those combination will give you NaAlO2, the Na plus and the AlO2 minus. The valences are balanced, right? So 8 of these are needed, as 8 of AlO2 minus are there, right? So all the 8 Na pluses are consumed there. So the final thing is just write in the 3 of NH3. No need to change anything with that because it is an uncharged species, right? So that is your balanced chemical reaction, right? Now is how we are supposed to copy the balanced chemical reaction. So thing is completed, no? So you can complete this stuff as well, and then you can do the right homework questions appearing at page number 31, right? Question number 10, right? Just complete this stuff first. Okay, so with this thing we are going to wind up the session for the day, right? Actually today we have discussed about the redox reactions, right? Fundamentals of the redox reactions. Actually redox reactions are mainly, right, due to the exchange of electrons, right, from one species to other species, right? To have some clear idea of redox reactions, we need the right knowledge of oxygen states. So we have started discussion with that thing, right? We had discussed how to come up with oxygen states of a given species, right? Given atom, right? So with use of that knowledge, we had ultimately came up with some balancing techniques of redox reactions, right? There are 2 balancing techniques are available with the redox reactions, right? So the first one is the half reaction balancing method, and the second one is the oxygen state oxygen number changing method, the direct method, right? So here we had ultimately discussed about the balancing redox reactions with the use of half reaction method, right? So next day we'll start our proceedings with the balancing of redox reactions using the direct balancing method, the oxygen state changing method, right? So until then, goodbye.